There is a moment, and I want you to sit with this for a second, when you step outside on a clear night and look up at the sky, and you feel as though the universe stretches outward forever in every direction, boundless and unending, a vast and infinite ocean of space. That feeling, that intuition is deeply human, and it is almost certainly wrong. The cosmos, as our best physics now tells us, has a horizon. It has a boundary. Not a wall, not a physical edge you could press your hand against, but a limit, a cosmic frontier beyond which nothing, not even light, not even information, can ever reach us. And what lies beyond that frontier is not empty space waiting to be explored. What lies beyond is something far stranger, something that challenges our most basic understanding of what the universe even is. To understand why the universe has an end, we have to begin with something Einstein handed us over a century ago. Space, Einstein showed us, is not a passive stage on which the drama of matter plays out. Space is dynamic. It bends, it curves, it stretches. And when we apply Einstein's equations to the universe as a whole, we find something that stopped physicists in their tracks. The universe is expanding. Every galaxy, every cluster of stars, every vast structure in the cosmos is moving away from every other structure. Not because the galaxies themselves are flying outward through space, but because the space between them is growing. Think of it this way. Imagine you draw two dots on the surface of a balloon. Now inflate that balloon. The dots move apart from each other. Neither dot is moving across the surface. The surface itself is expanding, carrying the dots with it. Our universe operates by the same principle, but in 3 dimensions of space rather than 2. Every point in the cosmos is being carried apart from every other point by the stretching of space itself. Now here is where things get genuinely astonishing. Because space is expanding, there is a speed at which distant regions of the universe can be receding from us. And that speed has no upper limit in the same way that the speed of a physical object does. 2 galaxies sufficiently far apart can be moving away from each other through the expansion of space faster than light. This is not a violation of Einstein's prohibition on faster than light travel. Objects are not moving through space faster than light. Space itself is carrying them apart. The distinction matters enormously. What this means is that beyond a certain distance, roughly 46 billion light years in every direction, the expansion of space is so rapid that no signal, no photon, no gravitational wave, no information of any kind emitted from beyond that distance can ever cross the gap and reach us. That boundary is called the observable universe. It is our cosmic horizon. It is, in the most profound sense, the end of the universe we will ever be able to know. But the story does not stop there, because that boundary is not static. It is changing. And this is where the discovery of dark energy enters the picture and makes everything more unsettling. In 1998, 2 teams of astronomers were studying a particular class of exploding stars, supernovae, that burn with a known intrinsic brightness. By measuring how dim they appeared to us, the astronomers could calculate how far away they were. And what they found overturned everything we thought we knew about the fate of the universe. The expansion of space was not slowing down under the influence of gravity, as most physicists expected. It was speeding up. Something was pushing the universe apart at an accelerating rate. We call that something dark energy. It fills every corner of space. It does not dilute as the universe expands. In fact, as space grows, the total amount of dark energy grows with it, because dark energy appears to be a property of space itself. And because it does not thin out, its repulsive effect on the expansion of the universe grows stronger over time. The consequence of this acceleration is profound, and if you spend time with it, genuinely moving. Because the expansion is speeding up. Distant galaxies are not just receding, they are accelerating away from us. Galaxies that are today just barely within our observable horizon will, over billions of years, be carried beyond it. The observable universe, the region of the cosmos we can see, is shrinking. Not because space is contracting, space continues to expand, but the accelerating expansion is constantly pushing more and more of what was once observable beyond the horizon, where light can no longer reach us. If you fast forward far enough into the future, tens of billions, hundreds of billions of years from now, all the galaxies beyond our own local cluster will have been swept so far beyond the horizon that their light can no longer reach us. An observer in the far future, standing where we stand, would look out at the night sky and see almost nothing. The stars in our own galaxy would still shine, but the vast cosmic web of other galaxies, the billions of galaxies we can see today with our telescopes, would be invisible. Not because they had been destroyed, but because they would be beyond the reach of any signal, beyond the end of what can ever be observed. That future observer, if they built telescopes and studied the sky and tried to deduce the nature of the universe, would reach a very different conclusion than we reach today. They would likely conclude that the universe consists of only our galaxy, surrounded by an emptiness that stretches forever. They would have no way of knowing from their position that the observable universe they inhabit is just a tiny sliver of a far larger cosmos that lies forever beyond their horizon. And this raises a question that I find almost unbearable in its implications. How do we know that we are not already in that position? How do we know that what we call the observable universe is not itself a thin slice of something vastly larger, most of which has already been swept beyond a horizon that our physics has not yet fully accounted for? The honest answer is that we do not know. We can only see what the speed of light and the age of the universe and the geometry of space-time allow us to see. Beyond the horizon, by definition, is a place our observations cannot reach. There is another dimension to the end of the universe, and it operates on a different time scale entirely. Thermodynamics, the science of heat and energy, tells us something unavoidable about the long-term future. The second law of thermodynamics states that the entropy of a closed system, its degree of disorder, tends to increase over time. Stars burn through their fuel and die. Black holes evaporate through a quantum process called Hawking radiation, converting their mass slowly into a trickle of thermal radiation and eventually vanishing. The energy of the universe over unimaginably vast stretches of time becomes more and more evenly distributed, more disordered, less capable of doing any useful work. Physicists call this final state heat death. It is a universe that has reached maximum entropy. A universe where the temperature everywhere is the same, a temperature astronomically close to absolute zero. A universe where no gradients of energy remain, no stars, no planets, no structures of any kind, only a thin and nearly featureless sea of radiation expanding through an ever-growing void. This is, according to our best understanding of thermodynamics and cosmology, the true and final end of the universe, But the timeline for this fate is staggering. We are talking about timescales that dwarf the current age of the universe by factors so enormous that ordinary numerical notation struggles to convey them. The current universe is roughly 14 billion years old. The last stars will die out in roughly 100 trillion years. Black holes will finish evaporating on timescales measured in numbers that require exponential notation even to write down. The heat death of the universe lies so far ahead in time that the mind genuinely cannot picture it in any concrete way. What we can do is hold the concept and let it work on us. The universe is not eternal. It had a beginning roughly 14 billion years ago in a state of extraordinarily low entropy and extraordinarily high energy. And it will have an end, not a wall, not a sudden stop, but a long and quiet dissipation into a state of maximum disorder where nothing more can happen. Between that beginning and that end, there is this: stars, galaxies, black holes, planets, oceans, life, minds capable of looking up at the sky and wondering about all of it. Now, there is one more layer to add to this picture, and it comes from a corner of theoretical physics that is still contested and still being worked out, but which has genuine mathematical weight. String theory and the broader framework of inflationary cosmology suggests something that, if correct, makes the horizon of our observable universe look not like the edge of everything, but like the edge of a single bubble in an infinite sea of bubbles. The idea of eternal inflation proposes that the quantum process that drove the rapid expansion of the early universe inflation never fully stopped. In most regions of space, inflation ended and settled into a slower expansion, creating what we call a universe, a region with its own physical constants and laws. But beyond those settled regions, the inflationary expansion continues, driving space apart at rates so extreme that even light cannot cross the gap. Other bubbles of settled space form within that eternally inflating background, each potentially with its own physics, its own constants, its own story. If this picture is correct, then the observable universe, everything within our cosmic horizon, is not the universe. It is a universe, one of perhaps an unimaginably large or even infinite number of such regions, each sealed off from the others by an inflationary expansion that can never be bridged. The end of our observable universe would be not the end of existence, but the end of our visibility, a wall of cosmic ignorance beyond which other whole universes exist, forever beyond our reach. I want to be careful here. Eternal inflation and the multiverse of bubble universes it predicts are not yet observationally confirmed. They may be, in principle, unconfirmable. But they arise from the same mathematical framework that predicted cosmic microwave background radiation, that predicted the large-scale structure of galaxy distribution, that predicted the accelerating expansion that observations confirmed in 1998. The framework has a track record. Whether its more speculative extensions are correct is a question physics is still grappling with. What we are left with then is a picture of extraordinary and uncomfortable complexity. The universe has a horizon, a limit to what can ever be observed. That horizon is shrinking as dark energy accelerates the expansion of space, carrying more and more of the cosmos beyond our reach. The universe has a thermodynamic fate, a long and gradual drift toward a state of maximum disorder where no energy gradient remains to drive any physical process, and the universe may itself be just one bubble in an eternal inflationary foam, surrounded by an infinity of other universes sealed away from us by the very physics that made our bubble possible. All of this comes from equations, from the geometry of curved spacetime that Einstein gave us, from the quantum fluctuations that seeded the large-scale structure of the cosmos, from the thermodynamic laws that govern how energy behaves over time. We did not find the end of the universe by looking through a telescope and seeing a wall. We found it by following the mathematics wherever it led, by trusting the equations even when they told us things that our intuitions resisted. That is perhaps the deepest thing physics has taught us about the universe. Our intuitions were built by evolution to navigate a world of medium-sized objects, moving at medium speeds under the influence of everyday forces. They are spectacularly poorly suited for understanding what happens at the edge of the observable universe or at the far end of cosmic time. Every time we have set aside intuition and followed the mathematics, the universe has turned out to be stranger, larger, and more astonishing than we imagined. The universe has an end, not a wall, not a boundary you could visit, but a horizon beyond which we will never see, and a future in which the structures we know will slowly and inevitably dissolve. And standing here in this brief and luminous moment, 14 billion years into the story, surrounded by galaxies we can still see and stars that still burn, the appropriate response is not despair. It is something closer to wonder, that we live in the one window of cosmic time when the universe is still legible to us, when the evidence is still there to be gathered, when the story of the cosmos can still be read,